Good morning or good afternoon, everyone, depending on where you are. Let me share my screen. Okay. Tracy, could you confirm that you see it well?
Yep, I see everything.
Okay. Okay, so welcome everyone. I just grab a laser pointer. Okay. Welcome everyone. My name is Adam Zsarnócai. I'm a postdoctoral researcher at the SimCenter. And in the next about 30 minutes, I will introduce you to our vision of damage and loss assessment and how we apply that using PELICUN. And then we hope that in the 20 minutes that follows, we will be able to have a lively Q&A with you. Please, Tracy already mentioned, submit your questions through the chat. She will triage them, and then we will try to answer them to the best of our abilities. So let me start. First, I would like to start from a little bit further away, step back. You saw in the previous 2 days that the SimCenter and we all are developing open source tools for you to facilitate your research and help you create complex simulation workflows from individual building level all the way up to a regional level that is demonstrated by these test beds that you've seen, particularly Atlantic City in Tracy's presentation yesterday. One of the big advantages of what we are doing is that we are developing these workflows to be extensible and modular. So depending on your research needs, you can pick the modules that you would like to use and then assemble a workflow that suits your research needs, and then effortlessly bring it to a supercomputer, design safe in particular, and run it there. And that gives you the possibility to run expensive computational fluid dynamics simulations on buildings and then potentially do loss assessment, damage assessment there. And this is what I'm going to talk about today, the damage and loss assessment part of the workflow and how we bring the same extensible and modular approach to that area using PELICUN. I will limit the scope of this presentation to wind hazards mostly. So although we come, or I come at least, from an earthquake engineering background, I try to expand PELICUN and the damage and loss assessment approach we have to different types of hazards, as you will see. And I will focus on how it applies to wind engineering and what opportunities do I see for bringing the current level of analysis to something higher and potentially achieving a tool that has capabilities to run performance-based wind engineering in the near future. Tracy has shown that we've done this level 1 type of analysis in the Atlantic City testbed, and we use the tool called PELICUN for that. And then we will use the same tool to bring it to a higher level. And I'm gonna show you now how we can use one tool to do different types of analysis at a regional scale. So first, let me talk about what we aspire PELICUN to be. What does PELICUN offer to the community? When we think about damage and loss assessment tools, we like to think in a 3-dimensional space that you can see here. We think about different types of hazards, different types of assets, such as buildings, bridges, infrastructure, and then different types of resolution, such as going from the building level all the way to the component level. And with PELICUN, we would like to create a unifying framework so that you don't need to use different tools for the different parts of this space, but we would have an open source tool that provides you multi-hazard and multi-fidelity modeling that can handle different types of assets within the same framework. This is different from what is currently available in the earthquake world and also in the wind engineering domain. And we believe that it's really helping collaboration between different domains and also within the wind engineering itself. Now, how does this fit into our regional simulation workflow that we call RWALE and we have mentioned that a couple of times previously. Let me start from the end result, and we will work our way back and show you where PELICUN is in this workflow. So starting from the end, what we want is to have decision variables available at a regional scale. These decision variables are something like the expected repair cost or repair time or the injuries in buildings. For each building, for each asset, to be even more generic, assets, again, are just a word we use for buildings, pipelines, power stations, all kinds of things, components in the built environment. So for each of these, we would like to have these decision variables available to help us understand the consequences of a particular event. Now, this is not enough in itself. We also need to know other pieces of information about these assets that are not directly caused or consequences of the earthquake, but more like descriptive features, such as if you are thinking about residential buildings, the number of stories that they have, the type of material they are made of, or even the socioeconomic background of the inhabitants. These pieces of data are often not available in a single database. So one thing that we do is that we have the publicly available asset information, and then we have a so-called exposure model that is also referred to here in Tracy's steps, the asset description, where we process this information and enhance it. We try to fill in the gaps to have an asset information model that is very similar to a building information model, or BIM, that you must have heard of before. So have this asset information model available for every asset in our analysis. Once we have that, and if we have the decision variables, we are good to go and discuss decision making or policy making and recovery simulation. Now, how do we get to the decision variables? For that, we need to understand the hazard or different scenarios of the particular type of event, say hurricanes in Atlantic City. And to do that, we usually have an understanding of the sources of the hazard, and then we have a hazard model like I shown here, and it's also here in the more high-level overview. So we have that hazard model, and that hazard model produces us intensity measures that describe the intensity of the hazard at various places in our region. This is just an example of that. This is a storm surge description in Atlantic City. So once we have that, for each asset, we have some understanding of its characteristics through the asset information model, and we have an understanding of the intensity of the particular scenario at that location. And then what we are doing, and this is a key thing in our workflow, is that we link the intensity measure and the asset information, and then do a damage and loss assessment step to arrive at the decision variables. We do this independently for each asset, because once we know these input data, the buildings don't need to know about each other to arrive at the consequences, the immediate consequences of an earthquake or a hurricane. And this allows us to run these simulations in parallel, embarrassingly parallel, and bring it to, say, design safe, and then save a lot of time and make these simulations easy or feasible to run, even at a regional scale, even with 2 million buildings. So what PELICUN does is it does this connection between the asset information, the intensity measure, and then provides a decision variable, if I'm trying to be very simplistic in its description. Now, what we would like to achieve, because in wind hazard or wind risk assessment, looking at HAZUS, for example, this is currently the level of the analysis. What we are aiming for is to include a response model here. So given the intensity, have some kind of estimation of the response, have some EDPs that are not wind speed, but rather some kind of pressure or other things that probably you are much better aware of what we should use there, and use those as descriptions of the intensity of the response of the building, and then come up with damages based on those results. I will talk about both approaches in the next step, but first let's look at under the hood of PELICUN and what happens in there. How do we get from intensity measures or EDPs to decision variables? What are the components that we need there? So if we look at only that independent part of the workflow, first, we can do this very simple assessment type, going from intensity measure using a loss model that is informed by the asset information to arrive at a decision variable. This is what's done in the flood damage and loss assessment in HAZUS. And actually, it's not really a damage and loss assessment, it's just loss assessment. Usually they use insurance claims data, so they know the losses, they fit some functions on top of that. And then depending on the type of building we're looking at, and depending on the height of the water, we can get the damage or the repair cost or the losses in the building. So that's the simplest possible approach. We can go one step above this by introducing damages in the process. So this is something like the earthquake damage and loss model in HAZUS. We start with an intensity measure, have a damage model. First, we have some damage states identified, and then given the damage states, we arrive at losses, which is going to be described by decision variables. And then the highest level that we are aware of at the moment is something like FEMA P58 for earthquakes, where, as I mentioned, we have a response model first, then use engineering demand parameters to describe the damage, so we have a more accurate, higher fidelity description of the damage, and then go to losses and then decision variables. So these are the three different types of analysis that we are thinking about. And what's an advantage of PELICUN is, as I mentioned, it's unifying these three. So you can choose which one you want to use, but you don't need to switch tools if you want to use a different one, which means that when you are running a regional assessment, you can use PELICUN and you can choose the level of fidelity you want to use for each particular building. So if you have a tall building, for example, in Atlantic City, you can choose to use response estimation and the high fidelity model there, while the buildings that are shorter and larger in number, you can still keep using a simplified model for the sake of efficiency, or maybe you just believe that that's sufficient for your research purposes. So this multi-fidelity analysis is a big advantage of this approach in our understanding. Now, what is PELICUN? I told you what it can do, how it fits in the workflow, but what is really this? What does this acronym mean, and what do we produce here? So I already told you it's an acronym, so it's probabilistic estimation of losses, injuries, and community resilience under natural disasters. That's what it stands for. And when we write it with all caps, we mean a conceptual framework for damage and loss assessment. So at that point, it's not really a tool, it's more like a theoretical logic behind damage and loss assessment. And we have a flowchart for that. And there's a paper I'm going to reference at the end of the presentation. If you are interested, I encourage you to read it, to learn more about this part of PELICUN. The other PELICUN with small letters is an open source Python library that's the implementation of this conceptual framework. When I say Python library, those of you who might not be familiar with Python might not know what that means. So here is an explanation of that. A library is something like a set of components or building blocks. In case of damage and loss assessment, we can think about those as like fragility models or loss functions or population distributions. And then you can pick the ones that you like. So that's the modular fashion that I mentioned at the beginning of the presentation. You can pick the ones you like and then put together an application that will fit your research needs, that's still using PELICUN, using this conceptual framework that I mentioned in the previous slide. Once you put that together, you can use it in the workflow that we have, either at a regional scale or at the individual building level. It's up to you how you use it and what kind of applications you put together. You are not all alone in this. We already have some predefined methods that are implemented in this framework. And those are the existing capabilities that are there. So once you download PELICUN, you can already use this to run certain types of assessments. That's what I'm going to talk about next. When we started developing this about 2 years ago, we started with FEMA P58 because starting from a higher fidelity, it's much easier to go down and increase the efficiency by simplifying certain things. So we started with P58. That's an earthquake-focused methodology that is only for buildings, and it provides a high fidelity approach, as I mentioned, we have all the damage and loss data related to P58 included in PELICUN. So we have fragility curves, consequence functions, all of that comes with PELICUN. If you want to do a FEMA P58 style assessment, you can run it just by describing the building and then see the results. That's how it started. Then we expanded in that space that I mentioned earlier. So first, we introduced different levels of resolution or fidelity by going to the HAZUS earthquake assessment approach for buildings. And that is a building level approach, so it's a bit different, much faster, much less computationally intensive. So that's how we first expanded in fidelity. Then we went to wind hazards and introduced the HAZUS wind damage and loss assessment approach. And then we also included different assets by introducing pipelines, which is very different in terms of the description of the assets than buildings. So that's where we are at the moment. And then I would like to emphasize that for all of these, we provide the supporting data. So if you want to do HAZUS style wind damage and loss assessment right now, you can download PELICUN. You have more than 3,000 or 4,000 different fragility functions there for wooden houses, and you can run the analysis right now without providing any extra data besides the type of the house that you want to look at. The reason I'm talking to you now and why we have this extra 20 minutes at the end of the presentation for questions and answers is that we would like to expand this even further this year. We would like to include water types of hazards, including storm surge in particular. And we would like to improve this part as well, but that's not really interesting for you. And then wind hazards, we would like to bring them up to a higher level in resolution and in fidelity. And I think there are a lot of opportunities there for us to work with you and to learn from you how you would like to do these assessments, and based on your experience with experimental testing and also virtual experiments and numerical analysis, what are the typical EDPs and how you would describe damage and how we can help you the most to do your research. So I would like to talk about my understanding of the opportunities in wind engineering, and then I'm interested in your opinion of these suggestions, and if you have some others, I would be very happy to hear them. So there are 3 topics that I would like to touch on. Increasing precision, so that's like increasing the resolution. Improving fidelity, which is something like improving the accuracy at a particular resolution. And then improving how wind hazards and wind damage assessment works with other hazards, storm surge in particular. So let's start with precision. In order to talk about this, first I need to give you a description of where we are at the moment, because I'm not sure all of you are running HAZUS style wind assessments. So HAZUS works in a very strange way when it comes to wind hazards. It starts with the same type of information that I mentioned before. So we have some intensity measures that we need to describe the intensity of the hazard. That's in particular in HAZUS, we have peak wind gust speed at 10 meters height in open terrain. So that's what comes in. And then we need asset information for those of you who might have an earthquake background and saw HAZUS earthquake methodology. This is a bit different because we have a lot of information that we need about the building. It's not enough to know that it's a wooden house with 1 story, but we need to know the structure type, the roof shape, the terrain roughness around the building, and then a lot of other parameters. I did not even list them all. You can see like secondary water resistance or the area of windows, tie downs, and so on. We need to know all of this to be able to identify which fragility curve to use. And then once we do that, we can pick one out of the more than 20,000 fragility curves in HAZUS. Each, or not, those are damage models, I would say, because each of them has 4 fragility curves, as you can see on the right side here, for the 4 different damage states that HAZUS uses. Now, these are not functions. They look like log normal CDF, but they are discrete points that come from a synthetic computer simulation that was done more than a decade ago. And they provide information about the probability of exceeding a particular damage state at each of 5 miles per hour increments in wind speed. And in between, you do linear interpolation. So that's how the damage is identified. And then the losses come from a different model. So the interesting thing about HAZUS, if you look at this figure at the top, is that we go to the damage model, we get the damage measure, and then we stop there. And then when we want to have losses, we go back to the intensity measure, go through a loss model, and then get losses. But the damages and the losses are not coupled. So the loss model will give you a particular mean loss ratio, again in 5 miles per hour increments based on the same computational simulation that they did about a decade ago. But those losses are not linked to the damage model. So if you have, say, 150 miles per hour wind, you see that we are looking at about 0.65 loss ratio here in this particular building. And then that could correspond to any of these damage states. So there is no link between them. Okay, so that's where we are now. And how can we improve on this? Well, this is a building level loss, building level damage. That's what HAZUS provides. One way to improve on this is just by looking at what computational simulations they did. I'm sure that it's possible to do this at a higher resolution, not at the building level, but at least at a subassembly level. That's what they did. That's how they got the building level damage information. You can see that they are linking different subassemblies and the damage in those subassemblies to arrive at building level damage states. So if we had such data available for a large number of buildings, then we could provide such fragility curves for different subassemblies and then describe the damage rather than in a building level. We can go and describe for different pieces within the building. This is very advantageous, not only because we know better what happens in the building, that's trivial, but as you will see later, it is also very good for working with other types of hazards, because when you have a flood, for example, it will damage different parts of the building than the wind, and it's much easier to avoid double counting there. I will return to this a little bit later. And then this is just one step. If you go further than that, we can introduce component level damage assessment, which is, for example, in this exterior wall case, we can disassemble it into a window, a stucco, and a door, and who knows what else is important there, and estimate the damages for each of those. And this is how we arrive at performance-based wind engineering, much like how performance-based earthquake engineering works today. So it's important to emphasize that PELICUN already supports all of these levels of analysis because it has been designed to do that for earthquakes. And all we need is the data, which is not a small thing to ask, I know, but at least the methods and the framework is there. So if you have done or are planning to do experiments that would provide this kind of data, then we would love to hear that from you and work with you to bring that to this platform, so that we have something to start with and then grow from there. Now, these steps provide us higher resolution, but higher resolution doesn't mean that the data that we get out of it is actually accurate. So how do we improve the fidelity? I also have a couple of examples for that. I mentioned that HAZUS has these two sets of models, one for the damage and one for the losses. One thing that we did already last year is that we used these raw data and coupled the damage and the losses. So you can see that here, these models were decoupled, and then our approach channels the flow through the damage measure, and then given the damage state, we evaluate the losses. Actually, you can see that these are very nicely fitting to the data, the log normal functions that we fit there. But more interestingly, given the damage states, we could calibrate loss ratios. So for each damage state, we have a particular amount of loss that we expect in the building, and using those loss ratios, we get back this loss function pretty accurately. So this is already available in PELICUN. This is a coupled approach, but it's still a building level assessment, and it's still using wind speeds to describe the damage and then the damage states to the losses. In order to get to a higher resolution, we also need to think about using something more descriptive of the damage, and that's going to be the engineering demand parameters. In particular, as far as I know, it's the pressure, the wind pressure at different parts of the building. So instead of having one wind speed value, we go down to more localized description of the hazard, of the event. I think this is much similar to using PGA, the ground acceleration for earthquakes, and replacing that with drifts or peak floor accelerations in the earthquake world. So this is an important step, and I think we have the experimental facilities and the virtual experiment capabilities to support this step and to run such analysis and have such data available so that we can have a better model for damage and a higher fidelity result at a higher resolution. And then finally, the next step, this is something Tracy is working on, she mentioned it yesterday, is to go beyond just using the simplistic damage models and fragility functions, and then connecting the different components within the building and allowing them to influence each other by having first a very detailed description of what is in the building and how they are interacting with each other. So that would be the highest level I can see at the moment. All right, so we've seen precision, we've seen fidelity. The last step is how to improve the combination with other hazards. Again, the baseline is HAZUS. So what HAZUS does is you calculate wind losses and storm surge losses independently. And then the challenge is how to make sure that you are not double counting damage. Let's say you have 60% loss in wind and you have 80% loss from flooding. So what is your loss from the two? It's definitely not 140%. And what they do, since their loss calculation is based on subassembly level computer simulations, they can disassemble these losses into each subassembly, disaggregate them. And at that level, they can easily see how they are interacting with each other and then come up with such tables for each building configuration where you look up your wind-only loss, you look up your flood-only loss, and then see what it translates to when the two things are acting together. Now, this is quite rigid. And whenever you introduce a new building type or you want to introduce something custom, this is not possible to adjust to it. So what we suggest is that going to the subassembly level, so having everything available at this level rather than at the building level, would make it much easier and much more flexible to directly couple the wind hazard and its consequences and the storm surge or flooding and its consequences. And also another important hazard is rain. If I know that the building roof cover is damaged, or I know that the windows are broken, it's much easier to anticipate rain losses due to rain, to the components, to the contents of the building. But if I only know a building level loss, it's very difficult to make accurate assumptions about how that will influence rain damage. So I believe we can go beyond this once we take a step to subassembly level analysis. So I hope this shows you how close we are to improving what is available in HAZUS. And another last piece of information I would like to share with you is that most of this will be available by the end of 2020. Most of the framework, I mean, of course, the data is something we would like to get to by working with you. But Frank has shown you the VUQ application just an hour ago or so. And that application already provides you the capability to run a particular wind event and see how it affects a structure in terms of the response. So you can get, say, the pressure at different places in the structure. This will be complemented with the PELICUN-based damage and loss assessment in the performance-based engineering application. This is an application that supports earthquake-related calculations at the moment, but it will support wind events by the end of 2020. So you don't need to run regional simulations to make this useful for your research. You can run a single building or even other, like communication towers or any kind of asset that you have a good model for, so that you can estimate the responses, and then use PELICUN to calibrate fragility and consequence functions, so that those could be used later, even at a regional analysis. And with that, I have a slide with different resources. So I think these slides will be shared with you. I encourage you to check them out if you have time. And I thank you for your attention.
All right, thanks, Adam. So as Adam suggested, we had allowed a little bit more time in this presentation to open the door for some discussion about the types of capabilities that one would like to see, that you would like to see in a tool like PELICUN to move us toward this ability to do these performance-based assessments of wind effects on structures. And so we'd open the chat now to conversation. What kind of capabilities would you like to see? Or as we build out the level of fidelity within the various modules that define this workflow, where do you think our most immediate effort should focus? Or possible ways that your work might be able to contribute to those advancements? So we'll kind of pause there and let people reflect and possibly share. And as they're pondering over that a bit, here we go. First one comes in. So shielding and channeling effects of buildings close together. So this idea of trying to capture some of the site-specific effects. That is one, it's a question of whether we have that in there. And the short answer is not to the level that one might hope for, meaning we account for the effects of exposure, but getting that kind of in-depth site-specific description of how the neighboring buildings, for example, modify the flow and the effects on the structure. Oops, sorry, my dog is a little yappy. Are not explicitly included. Adam, I'm going to mute while he's barking. Did you want to jump in and maybe engage our colleague a bit on this?
I can, sure. So let me just go back here a little bit to explain this. So yeah, here we are. So I think when it comes to the interaction of, or how one building affects the other at the region, right now, the intensity measures are evaluated before we go to individual building assessments. So those intensity measures can possibly capture these types of interactions. It depends on the hazard model that we use and what we know about the environment. So if we know everything about the buildings and how the geometry in 3D, and let's say we have the computational capacity to run a CFD for the entire city, we can use that. And then our intensity measures suddenly become the pressures, and we don't need to do this step. So that's a possibility. I don't see that as something feasible today, but maybe some people would disagree. What we do today is that we have these intensity measures that are typically wind speeds on open terrain. And then when we come to PELICUN, either straight or through these steps, we consider the terrain roughness around the building, which is, I know it's simplistic, but that's how we consider if it's in an urban region or in the middle of nowhere.
Yeah. Thank you, Adam, for fielding that while my dog went a little bit crazy. But I think this also represents a really excellent opportunity, right? As Adam suggested, being able to run full CFD on the regional scale that we're looking at with these kinds of test beds could be challenging. But I think one interesting area of opportunity is to think about how we can make a kind of hybrid approach that meshes, for example, these things together so that you're running the test bed with a more simplified description of the exposure. We are currently able to extract that from land use, land cover data. But you're also aware from our presentations yesterday how tools like Braille's allow us to extract imagery or about all the buildings for which we have parcel information and building photographs from things like Street View to capture a geometric description of everyone next to you. So in theory, if you wanted to pick a footprint, a set of footprints of buildings in the immediate vicinity and run a higher fidelity simulation locally there to capture local wind effects and nest that within the larger simulation where we're using a more crude approach to account for that kind of interaction effect, that kind of local topography using land use line cover, then I think that that kind of nested simulation creates an interesting opportunity that is currently not in the framework, but could be a way to contribute. Sorry, we have a repairman working at the house, and for some reason my dog forgets that he's met him 15 times today, but each interaction is apparently novel. So I hope that that answered that first question. There's another question that's come in. Can you clarify if PELICUN works with damage assessment imagery data or just structural response from numerical and experimental simulations? So I don't know, Adam, if you want to jump in it, I could jump on it too.
I'm trying to understand the question to make sure I answer the right question. So Tracy, if you have something to say, maybe you should start and then let's see.
Yeah, so what I would say right now, Mal, is that the way it's structured currently is that all the representations of the structure and the simulation of damage happen in an entirely computational manner. The pristine structure from the building inventory, no damage, is pushed through the simulation, exposed to the hazard intensity. Its corresponding level of response or the exposure then results in some level of damage, and it moves through the workflow completely using computational simulation and not mashing up any kind of actual damage that may have occurred in the event that you were trying to hindcast, let's say, performance based on some full-scale observations after an event. Now, with that being said, there is an exciting opportunity to look at how the Braille's tool that's currently being used to extract various geometric and building information from photographs could be used as a part of a more integrated loop that takes real damage photographs from field reconnaissance, processes them to get some indicators of component level losses, and then compares that against the result of the simulation, and can be used to calibrate, as Greg suggested in the conversations yesterday, the model. So currently right now there is no infusion of full-scale observations or field observations of damage. It is an entirely simulated workflow. But it does seem interesting to consider how we could take some of the capabilities used to digitize our inventory and use them as part of a model validation framework. Adam, I don't know if you want to jump in.
Yeah, I just want to, I agree completely. I think what I described today is how we do the simulation. I think those imagery that is available from past disasters would be useful for calibration, as Tracy mentioned. So in that case, we have to think about the computational costs, because calibration at the city scale, running this simulation possibly thousands or tens of thousands of times, could be very expensive. But yeah, I think it's possible. There are solutions, there are surrogate models, there are ways to work around that, and then that would inform the damage models, so that could help us develop better ones. And PELICUN can help with the calibration once the data is available. But as Tracy mentioned, first we need something like Braille's to extract the data from the images.
All right, Greg has just jumped in. So basically so Greg has asked, are you aware of any efforts to systematically collect damage and loss fragility models for wind or storm surge for various types of components and buildings? I think to answer this question, and perhaps I'll nest it in another angle, there was a great benefit, as Adam mentioned, of having P58 as a kind of a one-stop shop that was already nicely organized and advanced through the work that previously occurred in the earthquake engineering community, to bring that directly in and have all of that at our disposal. And now the question becomes, is there a similar effort in the wind community that would be collecting or developing these necessary damage and loss fragility models so that we could get to the level of fidelity we are hoping for? So I think we're going to open this up more for a point of conversation. A lot of my instincts tell me this is going to be mined from the individual efforts of researchers like you and the work they're publishing, and some of the work that's being derived by looking at these large-scale sampling efforts after major disasters to document performance and try to reconstruct some of this from those observations. But outside of the public loss models, is anyone aware of an open effort, if you will, to compile and aggregate this kind of information? And I will pause and allow some pondering of that. But I think the word being systematic there. I mean, I can say for our part in STEER, a lot of what we're trying to do is through having standards on the way that we are assessing component level losses, we're able to generate data that could be used for that purpose. One of the downsides of our STEER approach, even though we systematically sample after the events, is you're dependent on the occurrence of these events and having the chance to sample or collect enough data to statistically, capture performance over a large range of intensities and different typologies with various underlying vulnerabilities. And it just turns out you need a lot of data to do that well. I think the Harvey data collection was probably the most ambitious in this regard, in that it worked along the gradient of hazard intensity and therefore could start to try to reconstruct this from a singular event. But we are still probably a ways away from having enough data to do a good job of this, at least through the hurricanes we've seen to date. I'm gonna let Greg's question float there because I think it's notable, and we welcome in the chat any continued engagement on that. Another question Amal asks, can users define the wind field of interest, including bringing in things like tornadoes and downbursts? So this is an area we had not officially ventured into. We started by taking the hurricane testbed, as its name suggests, and bringing that type of, of wind field, if you will, into the simulation. The framework itself, in theory, would not have a problem accommodating other types of hazards or other types of, wind events like a downburst or tornado. Interestingly, those are also probably more extensible to a more efficient simulation as they're more localized. Part of the reason we have these nice big hurricane testbed is the spatial extent of that wind field and allowing us to do 80,000, 100,000 or more buildings to show that scalability. But I think it is interesting to consider how we could pick a much more compact path and use this to examine these more localized wind events. Adam, what's your reaction to thinking about extending this to other wind classes that are a little more concentrated?
I would use, again, this figure that I have here to show that whenever you are talking about a different hazard, that comes here. So before the actual damage and loss assessment, if you have a hazard model for that hurricane or downburst and you can provide intensity measures, then we can accommodate that, because as far as PELICUN is concerned, it needs some description of the intensity and then use the damage models to arrive at the damage and loss. So it's very generic. So it depends on if you have damage models, I mean the parameters for those models, or you have some kind of experimental data so that we can work on calibrating models to that. And I'm pretty sure you have it. I mean, there are so many experiments done. There are so many labs. It's just connecting the dots and connecting the people and then doing these calibrations. And we are happy to help you with that. Or I speak for myself. I am very happy to help you with that.
And I think this raises a very important point, right? The whole idea of lifting up these test beds is to create, like I called it yesterday, the computational scaffolding that you could use to bring in what you want to study, right? And so the idea is the inputs, outputs that have to flow between each of these, boxes in Adam's diagram, once they're constructed and the workflow is erected and shared, and these are all open and available in GitHub, then you have the ability as a user to come and shift the direction of that test bed and bring in some different features. And that kind of parlays into the question that Maria asked about going to the Caribbean. There should be no reason that the testbed couldn't be extended to other regions. And here's a couple things to think about when you're thinking of extending it somewhere else. Number one, do we have good inventory data? One of the strategic reasons of picking the Atlantic City testbed or New Jersey is they had a lot of great open data. For the earthquake testbeds they ran, they had the urban sim results. the reason I point this out is you need to have some good data on the inventory, ideally high quality data or fairly complete data, to be able to start generating descriptions of these structures. So that's the first thing I'd point out. The second is, do we have meaningful hazard simulations for these areas, which would again require having bathymetry and topography, land use, land cover, all the things you need to drive that wind field or storm surge in that area. For the Caribbean, and knowing where Maria's from, you know, some of that already exists, at least hindcast results for Maria that are available, including the ARA wind fields, which are in design safe now, and some of the ADCIRC simulations, I believe, are also posted. So you next want to look for, do I have a good way to either simulate the hazard with the right, you know, data that I would need for the exposure and other features that I want to simulate, or are those runs already done somewhere and I'm going to do a historical event or a synthetic event, but that data is available. Once you kind of get over those two hurdles, I'd say the last hurdle you have to jump through is, are there appropriate descriptions then, you know, do I have the fragilities I need, in other words? And that's where things get tricky, right? One of the tricks that we're doing with the New Jersey testbed is, because we can enforce code compliance, and they have a high rate of code compliance, at least according to IBHS, we are able to take some rule sets and prescribe how we think they're going to perform, and the topologies are well documented in HAZUS. And therefore, we have ways of describing their likely performance, levels of damage, and associated loss. In the Caribbean, we'd have to start asking questions about, does that data exist that captures how the state of construction in these areas would perform? Do we have damage and loss data? Do we think there's a high level of compliance? And I know, Maria, we struggled with that in the Caribbean consistently, because now all of a sudden you might have to propagate some different levels of uncertainty through that simulation, knowing that all the buildings may not be to a set code or may not perform in a prescriptive way because they're not complying with some minimum standard. Right, we agree with each other. And the typologies are dramatically different. It's not to say it's not doable, but a different set of assumptions, and even more importantly, decisions about uncertainty propagation would be necessary. But I think that's the cool part, is that once, again, the scaffolding's there, you can go do this kind of work, and as a researcher, show some real expertise in how you would model a unique environment. And as Maria is saying, one that has a multi-hazard, you know, so that makes it really exciting. Yeah. Adam, I kind of grabbed that one because I could sense a lot with Maria coming from Puerto Rico, some of the things she might be interested in.
That was perfect. I agree with you.
Yeah, and so there's a couple other questions. Sanjay asked a question about, is it any different from running the Atlantic City testbed? I think for yeah, do you want to jump on that one then?
Yeah, I think I can answer that real quick. I just wanted to be careful about the damages from tornadoes and downbursts versus the damages from hurricanes. So although it's both wind, I can imagine that the damage, at least when we look at it at the building level, would be described by different fragility functions. So you cannot just take the hurricane fragilities and apply them in a tornado. I'm not sure. So at least when we are at the building level, if we go to a higher resolution, then suddenly we don't have to be so careful, I think, once we have pressures or once we have something even more granular.
But it kind of it represents a really good point. As you imagine uses and extensions of the testbed, you kind of have to step through the chain. You can go through the, the 5 colored boxes at a meta level and just start to think about whether the necessary data or models are available for that. And there are some that have been developed, especially in the forensic evaluations after tornadoes, that help to capture those levels of damage. Another question, industrial systems, open structures with equipment, pipes, cables, transmission, offshore. Yeah, I mean, this kind of was like your pipelines block, but this other type of distributed infrastructure, which we know also has challenges. Adam, what are your dreams for that in Pelican?
I would love to. So when I show this, one of the things I miss from here is having a box in the background here, like wind and pipelines, or wind and not really pipelines, because that's I don't really expect, but let's say wind and transmission towers. I don't know about any fragilities there. If there is data, I would love to.
Yeah. Yeah, there definitely is. So the lifelines and electrical power systems and other things, they're definitely ones that could come in doing these more networked models.
We can support it as long as you have some kind of a logic that starts with an intensity. Then you have a function. It doesn't have to be log normal. It doesn't have to be normal. It can be anything. You have some model that describes the damage state as a function of the intensity. If there is something like that, I can bring it in PELICUN. Basically, it's that simple. It doesn't have to be a building. It doesn't have to be even a structure. It can be anything.
Well, I think that's awesome. We are out of time for this session, but it's a perfect segue into the next section. Imagine, if you will, how you could bring your research in, make your next proposal so much more competitive, because you're possibly not only leveraging the Wall of Wind's EF capabilities and writing an excellent proposal, which is what our next session is all about, but even showing how you can parlay that into the workflows of the SimCenter, for example, into these regional test beds to really amplify the reach and impact. The chat showed how specific questions or applications could really shine lights that the community hasn't really looked at before. Now with this available as a scaffolding to build off of, it might help you to reimagine ways to actually recraft your proposal to have even greater, broader impacts by working with both facilities. So with that, I'll thank you, Adam, for the presentation. And I will transition now. I think we are going to Rindam, who's going to talk about how to go win that NSF proposal. And he knows how to get this done. He's very skilled in that area.